Okay, so just to get you further equipped for the lab today, I just want to lead to the algorithm that the discussion today in lab would lead to. I was trying to illustrate everything through this very nice simple example where you have basically people are trying to jump off a cliff into a water body, and there are two states corresponding to S1, which is basically cliff, and S2 is off the cliff. It's on cliff, or we call it horizontal movement on the cliff. S2 is off the cliff, which will basically mean a descent or a fall. And we saw this transition S1, S2. There were two possible actions that you could lead you to from S1 to S2. One is either you could simply walk off the cliff, a very dangerous thing to do, and the other is you could slide down the cliff, and once you are off the cliff, you are basically on a free fall, and that's with probability 1, but obviously you incur a negative reward because you could have probably slided off and be safer, but once you are off the cliff, there is danger in every step. And then you could also be on S1 itself. S1 had this A11 going to itself, which is you could just walk on the cliff. Okay, so I was trying to give this simple example, and yeah, this is not too non-realistic because you take sufficient extensions to this model, you can get applications of reinforcement learning to aerobatic helicopter flight, for example. And what determines which action I will take in which state, that is the policy. We talked about the deterministic policy, and we said we will initially focus on a deterministic policy. The reward signal is associated with this transition. So we said that there would be a reward, for example. So I have been generally using blue for policy, and let me use red for reward. So you could have a reward of 5 when you are back on state 5, or using action A11 when you walk from S1 to S2, a reward of 5, a reward of 10 when you are sliding, which is much safer than walking off a cliff, but once you are off the cliff, it is danger -1, right? And then there is a probability associated with this entire process. That is the other part. We also associated these probabilities, 0.5 of looping around, 0.5 of walking off the cliff, but if you are sliding, you are certainly from S1 to S2, that is probability 1, and probability 1 of basically moving back to state S2. If you are on a fall, you are on a fall, right? You can't walk while falling. Even if you walk while falling, you are falling. I mean, we had a sufficient discussion on this. And then we said, well, all this starts making impact when we start talking about cumulative rewards, long-term rewards. And we had this accumulator GT across time. So these are immediate rewards, but you could just add them. GT says I am going to add the reward you get here and the reward you get here based on what path I follow. So GT feeds in from a path based on policy, and basically based on that it just sums the RTs. The rewards are based on the path. Okay, and then we had a discussion on what are the alternatives. All of these suggestions came from you. So based on the suggestion, we said let us try and look at the maximizing the expected return, not just the return but the expected return, where this expectation is based on the transition probabilities, right, and a particular policy pi. V pi is the expected cumulative reward under pi. In plain words, that is the definition. So we had considered two pies, for example. One is if you are on land, always slide, that was pi 2. Another pi 1 was if you are on land, always walk, which means you could either walk on the land or you could land up walking off the cliff, the land. Okay, so under a particular policy, you could look at the expected return, and that's a function of the state. The state from where you begin is where you look at the expectation from. Okay, so this much we had done, and then we noticed a very interesting thing which is highlighted in red there, and I want to bring that to your, this part in red is basically the basis of your assignment today. So let me write that again. B pi S is, the remaining part is summation over S prime in S of probability of S prime given A comma S into, there's a big square bracket here, the reward you get when you go from S to S prime based on action A, plus another component. So this is what happens when you move from S based on A to S prime, and based on some A prime you move to S double prime, and so on, right? So this part, the part that follows here, is written here in red, and that is the probability of going from S prime to S double prime under action A prime, is A prime comma S prime, into the reward of going from S prime using action A to S double prime, and so on. Okay, so this whole thing and so on So what we start noticing at this point from an algorithmic point of view is this part red, which has actually kind of recurred again. It is just that the whole thing is now episode is repeating from S prime rather than from S. Okay. The goal is basically to find a policy pi that maximizes this expected cumulative reward. And I illustrated in the class what happens if V pi, for example, you compute only till a n time steps. This is where we left off in the class. We said that for this simple example, you could have, if you want to compute in 3 time steps, starting at state S1, under policy pi 1, what is the expected cumulative reward? You will have to factor in the probability of transitioning from S1 to S2 and then looping around S2. That is one path under pi 1, right? Because pi 1 says, if when in S1 always choose A11, when you are on the cliff always walk, right? That was our pi 1. Whether you walk on the cliff or walk off the cliff, that's based on your fate, but you do that. So this is one path. The green part we highlighted was the other path, which is I might keep walking around in S1 itself. I might keep walking around the cliff and safely remain on the cliff, right? So this gives you the other trajectory. So the sum of these two is the V pi 1 S1 comma 3. This is up to a path length of 3. You could do this for 5 as well, right? You might transition from S1 to S2 in 1 and then loop around 3 times, so that by the 5th time step you are in S2, and because you are looping around in S2 is with probability 1 incurring a reward of -1 in every action you take, it will be -1 3 times. So 5 minus 3, here you had 5 minus 1, now it's 5 minus 3 for this path. Okay, this is analogous to the previous case, it's the same idea. And now we have a couple of other cases. The green part is the other extreme case. The green path is basically a looping around S1. The one in middle is the new case. And what does this middle path correspond to? Anyone? V pi 1 S1 5. What does this correspond to? So you're doing 2 S1s, right, and then 2 S2s. S1 to S1 to S1, and then you go to S2, S2, right. So that by the 5th time step you are in S2. Is that correct? So you can see that these probabilities have a compounding multiplying effect, right. It's half, then 1 by 4, 1 by 8, and that's exactly algorithmically what we observe. If instead of 3 or 5, now if you had infinity, think of this as infinity, right, what would happen? Some kind of recursive structure, okay. So the whole purpose of this computation is for you to realize the recursive structure. This one, the 1 by 4, 1 by 8, okay, 1 by 4 is clear to you, right. 1 by 4 is, I loop around twice in S1, I safely walk on the cliff twice, and then I land up walking off the cliff, and once I am off the cliff I am on a free fall. So there are 2 instances, 2 time steps where I am free falling, 2 time steps where walking, one here, loop back, and one here. So that's how I get the 1 by 4. The last one is 1 by 8 because I have moved here. Wait a second. So what have I done? Sorry, the other way. I keep moving back in S1. The last case is with 0.5 probability I move back to S1. Again 0.5 probability move back to S1. I do this 4 times. So should it be? Oh, should be 1 by 16? That's a mistake. Sorry. In this one? Yeah, of course it goes to S2. Yeah, this goes to S2. Let me actually write down. Right? So, yes, it's very much like the previous case. Let me write this down. This is S1, A11, S1, A11, S1, A11, and now what I do is I could go to A1 to S1 or A1 using action A12 to S2. Yeah, and then this. Sorry, this is not A1. This is not A12. I mean, this part I missed. Okay, so from S1 3 times, third one in the, yeah, so here I landed up in S2, here I have not gone to S2 so far, I mean I have gone to S2 only in the final step, only wondering why I didn't, there should be 1 more 1 by 2, right, so I probably that's, yeah, there should be 1 by 16, you're right. Yeah, so then these should be, if I correct this to 1 by 4 and 1 by 16, does that help? Yeah. One more term for what? This term is okay, right? For this one is okay, it should be 1 by 4. The second one, the 1 by 16, and you are saying there should be one more. Where, yeah, I think this is missing one term, where you walk around S1 3 times. Yes, that's missing here, right? That will be 2 S1s. 2S1 plus, right. Oh, then this should also be 1 by 1 half, right? No, but by the way, this is pi 1. This pi 1, policy pi 1 doesn't allow A12 at all. So, you're right. Okay, so I had written it correctly, I don't know why I changed it. Okay, so this was right, this was also right. I was only missing an additional term, that's all, yeah. This was right. And this is, what I wrote earlier was correct. Yeah, this is all correct. The only mistake I had made earlier was I transitioned from S1 to S2 using A12, which was meaningless. So this is this guy, correct. Does that help? The third term, this third term which you are asking for, 1 by 8, corresponds to moving to S1 3 times. In the fourth step, you can either branch off to S1 with A11 or to S2 to also using A11. So the two basically add up to 1, and each of them, this is 5 and this is also 5. So 5 into 0.5 plus 5 into 0.5. So that gives you 5 plus 5 plus 5, right? Pardon? All these will be 1 by 2. 1 by 8, right? It is 1 by 8. Okay, I mean, maybe you should verify it once more, but 1 by 16 only. Okay, so then we can just correct it. But this path is what I have explained on the board now is correct, just that number. So this should indeed be 1 by 4 and then 1 by 16. Is that okay? So but this explanation is important. Why is it 1 by 16 whatever? Why is this 20 here, right? So it's 20 is because of these 4 steps. Each of them contribute to 5. Okay. Is that okay? Does it tally with what you wrote? You were getting 1 by 8, but is this? No, but then there is, but this sum. So this is 5 into 0.5, 5 into 0.5, 5 into 0.5. Okay, again back to 1 by 8, 5. Is actually 1 by 8, yes. What I had written earlier was correct. Again, you are right. Final, this is final. Okay, so, again, these 2 0.5s add up to 1, right? So it's not just this 0.5, this 0.5 plus this 0.5. So this is correct. All I was doing is missing out one additional term. You can likewise compute this V pi for pi 2 under 3 and 5 transitions. So now let me come to the main part for today's lab. So one of the suggestions that you had given was, why not have a discount factor, right? Discount the previous rewards. So for example, if gamma is a multiplicative discount factor between 0 and 1, you could just multiply the previous rewards. The idea is to trade off the importance of immediate versus long term rewards, right? So this is this effect of discounting the immediate old rewards to keep in mind a long term reward. So this why is this V pi as interesting? You are basically evaluating the desirability of every state. How desirable is the state? How much value do I associate with a particular state? And you can use V pi also to choose an action, like the series of actions. you can choose not just action, but you could choose a policy as well, right, which give me that pi which will maximize the value associated with this state. So when I say choose between actions, that is select pi, and this is your assignment basically. So select actions to maximize value. And now, and the structure you want to use in your assignment is exactly what I have written here. V pi s is summation over all the possible next states, right. So you are saying that I could have gone from S to any S prime, and once the probability associated with this transition based on an action A will be multiplied overall with the expected with the reward I would have thereafter. What is the reward I would have thereafter? The reward associated with this transition I already count. Okay, this is the reward already associated with the transition, and this is the reward I would have thereafter, discounted suitably using gamma. Okay, so this is the reward now and here, and this part is the box. So this part is a shaded part here. But I have now discounted using gamma. So this is the basis of Bellman's equation, and that's what you need to solve in your assignment. Have you ever come across fixed point iterations, fixed points? You have done that, right? In which context? Stochastic equations, right? So this has the same flavor. Sometimes people also talk about the Q function. Q function is the expected return on action A from state S. So value function was looking at state S. Q function says I am going to fix state S and also the action from state S. Thereafter I am going to look at the expected cumulative reward. Okay, it's the same idea, but now return on action A from a state S. These two have been fixed. Two things have been fixed. So you can contrast this against V. Sometimes people use Q instead of V. So select actions to maximize the Q function. Okay, both of these exist largely for historical reasons. Okay, so I am going to jump to the others are just setting you the context. So formally this is a Markov decision process. Okay, what do you have? You have first Markovian property, where probability of state given the next state given the previous state is the same as the probability of the next state given the entire history, right? So you might be given an entire history, doesn't matter when you make the Markovian assumption. St includes st minus 1 and so on. So this Markov we talked about in the class already. That's the first thing. Then you have actions from states, probabilities of transitions, rewards and gamma. And what we are exploiting is the Bellman equation, where we have this recursive structure, okay, where V pi s is computed again in terms of V pi s. This is the equation that we are exploiting. V pi s is expected value with respect to reward at the next step t plus 1 plus gamma times the V pi from state st plus 1. Okay, this is a structure, recursive structure. That's the main idea. So this is what we were expanding so far in red, the recursive structure here. And let me jump to the value iteration algorithm itself. So this is what the algorithm that you will implement is basically this idea that if this is the kind of steady state fixed point I expect, can I do the following? Can I start with some initial guess of the values? So what we want is a V star. So V star is the highest possible value we could have ever had. So instead of just the expected value, imagine that you wanted to maximize over all possible actions or all possible policies the cumulative expected reward. So that corresponds to V star. Okay, so V star has this additional max over all possible policies. So V pi already had this structure which I have written on the board as well. V pi s is expected expectation under the choice of a particular policy pi, and the transition probabilities of the reward at the next step, followed by a gamma discounted version of the same expected cumulative reward of the value function. All you now do is, if I take a max everywhere, what happens? We have a similar equation. So V star s is max over A of the expected reward, cumulative reward, but with that expected cumulative reward can be looked up in terms of the reward in the next step plus V star. V star is again the max value, the same max expression that we have written on the left side, but evaluated at the next state, st plus 1. Okay, so your goal is to discover this. So the algorithms are designed by basically exploiting these equations, this 3 and 4. The 3 and 4 are the crux. So either you look at V pi s or you look at the V star, which is the max, the most possible, the highest value you could have got under all choices of policies. And here's the algorithm. So you start with the initial guess of the value function and then plug in that value as you keep updating the value of t. So you set t to 0 and update the value of V star at t plus 1th guess of V star using the tth guess of V star. But this tth guess of V star you accumulate it from all the possible next states that S could have gone to. Okay, so this is S, this is S prime under action A. So like before, you are accumulating the value at S here by looking at all the possible S primes that S could have transitioned to and accumulating the discounted value, discounted reward, cumulative expected reward from S primes. This is the basic idea of the algorithm. Now let's take the simple example. This is the environment state for a maze. Let's say, okay, you have a maze that you need to solve. Now the agent doesn't have this full view. Agent only has a partial view of it. So this is the agent state. This is the agent state, whereas this would be the environment state. So when you write your program, we are basically for us the world will be our agent state. The environment has a role to play in our agent state. We won't have access to the environment state, so we are only dealing with the agent state here. Okay, so in general, agent state is different from and typically much smaller than the environment state, as we saw in the maze problem, and that's what determines the actions. So you can construct the state basically using the entire sequence of states, actions, rewards and so on, right? The environment state may be invisible and is actually often not completely relevant to the agent, the entire maze that you saw. So if the environment is fully observable and that we assume is the agent state, then the agent is in a Markov decision process. So effectively in a Markov decision process, I am very happy with my small world. That's the idea of Markov decision process. Now if you start bothering about what the environment state is and try and model that as well, then you have a partially observed Markov decision process. So that's why the title of your programming assignment is just Markov decision process. We are only interested in modeling the agent state. I mean, just to give you one small example here, if the agent was here versus here, would the agent ever know the difference between these two? The agent would never know the difference between these two, right? But we are not concerned, we are not trying to overcome this issue in this assignment. I mean, in a more challenging scenario, you would say, oh no, I am interested in distinguishing, so I will now consider the actual environment, try and model it, but we are not looking at that right now. For us, we are not bothered about this scenario right away. This can be an issue. There were a couple of inquiries on just revisiting what we discussed. If you were somehow not aligned with the discussion so far, please pay attention. The core concept here is that you have an agent interacting with an environment, and we are largely talking about the agent state, right, ST, and the environment basically interacts with the agent through the agent's decision to perform an action. And I gave this example of bicycling. When we are learning how to bicycle, the angle at which we adjust the bicycle, for example, is an action we take, and based on that and based on the coefficient of friction, for example, of the road, the environment gives a particular feedback to us by which we move to the next state. Either the bicycle topples off, or we are able to balance it. And the core idea here is that there is some delayed reward, our understanding of whether the action is correct or not is only in retrospect. Only after taking the action do we know whether we took the right step or not. Okay, so we started with this very nice simple example of people jumping off a cliff. There are two states, the cliff and basically on the cliff and off the cliff. These are the two states we talked of, and we said that the actions could be walking, sliding, falling, and leading to transition from S1 to S2 or staying on S2. So in the class we spent significant time on this, and we said that one way you can design your transition probabilities and rewards is as explained on the board here. Once you are on the fall, you are on the fall, but otherwise you could be walking on the cliff or walking off the cliff, right? So from S1 you can transition to S2, but from S2 you don't transition back to S1 again, and that's what we see in this picture here. And based on this, we said, well, we are not interested only in the immediate reward. I want to know what is the safest way of descending into the water from the cliff, and I would like to incorporate a long-term rewards or cumulative rewards. So cumulative reward is what return, the GT is GT accumulated from RT plus 1, the reward at next time, the reward thereafter, and so on. So that's cumulative. And in the class we invited suggestions on what will be a limitation of just trying maximizing the return, the cumulative reward. And the suggestions came where, for example, instead of just doing cumulative over infinity, why not do cumulative over n steps? That was one. Second is damp previous rewards. I mean, history should be kind of damped off. And the third suggestion was, why not do a non-linear combination of rewards? So the first two suggestions are things that we have already talked about, which is we talked of a value function, and we said that the value function could actually consider not only accumulated reward but expectation, right? So there is an expectation factor which takes into account probabilities of transitions, and that itself has some damping effect also. So less probable paths will be given less weightage, more probable paths will be given more weightage. So that's the expected return or expected long-term reward or expected cumulative reward, that is called value function. And we can also look at value over n steps, not necessarily leading to infinity. Okay, so we did that computation explicitly for this example we took in class. I spent some time today in the lab as well. Again, I don't think we'll be going over this computation again, but the important take home from this computation is that there is some recursive structure, you see, right? If you look at this path S1, 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 the green component here, we find that after a point you are basically multiplying probabilities with following paths, right? So probability of going from S1 to S1 using A11 into whatever happened here, right? So this structure, this substructure is what we want to use in our algorithm, this recursive substructure property. So I think that is the main take home from this. So I would encourage you to try out the tutorial problem 1, where we develop further on this example. You are asked to find the optimal path, and it will really be nice to work this out with pen and paper if you are not able to relate to some of the details, though we worked out most of it in the class here. Okay, so that's a basic idea, and now thereafter we just write down the value function in its full form. We also incorporate the discount factors. So a value function is parameterized by a policy which determines what actions to take at which states, and the discount factor kind of dampens the previously accumulated rewards. So it trades of importance of immediate versus long term reward, and here is where we based on our working out on pen and paper, we started realizing that some components repeat themselves, especially when you are now looking at really long term, not restricted by any n, but really long term rewards. This component v pi s actually repeats itself here. That was the main finding here, right? This entire component is repeated. I have not marked it here, but I have marked it in other places, that this component is nothing but v pi, but now it's not just v pi, it's v pi s, it's v pi s prime, right? When you consider transition from S to S prime using A, you are now utilizing the work done from S prime, the value at S prime. If you want more examples, you could think of financial investment may take months to mature, and that's why v pi s becomes important. You're looking at cumulative expected long-term rewards. Refueling a helicopter, so you may be tempted to keep on flying a helicopter until the fuel tank is empty, but that's a very stupid decision. So that's where the trade-off between immediate and long-term becomes very evident. Or blocking opponent moves. If you have played chess, so you instead of being myopic and trying to win in every step, you may want to kind of strangle the opponent or disallow the opponent from having paths that would lead to that person's victory, right? So I also talked about the Q function. The Q function is nothing but a way of looking at the value function, but from the perspective of an action that you take from a particular state S. So if you have S to S prime path using A transition, right? So your value function was completely focused on the cumulative long-term reward, expected cumulative long-term reward from S, but the Q function says I am not just interested in that, I want to see what effect the choice of A from S would have. Okay, so you are looking at the combined effect of S and A, but otherwise it is the same. So QSA and V pi S are largely for historical reasons, both exist, and perhaps I will build on the Q function in the next class. And just to again illustrate that you may have your agent state. Agent state is really a small component of the entire environment state, and the agent state is what determines the actions. In the case of Markov decision processes, we assume that the agent state, environment state is fully observable and coincides with the agent state. So we don't really take extra efforts to model the environment state, right? So for us, and I again went over this example in the lab, we are not concerned with modeling the environment state so that agent is able to distinguish between these two very similar looking states. We don't concern ourselves. If agent is stuck and cannot distinguish, so be it. That's the idea of MDPs here. And the other aspect is also that MDP, right from the beginning of the class today, we have been saying the use of the word Markov is because you are only concerned with the immediate one level transition, S1 to S2. I am not concerned with the entire history so far. So the probability of visiting S from ST given an action AT is the probability of visiting S given the entire history before S, comma AT. Okay, so this is again common to Markov hidden Markov model also, which we discussed earlier. Finally, coming to your algorithm, we said that this recursive structure is what we want to exploit, not only for computing the value function. This recursive structure gives you the Bellman equation. So you can use this recursive structure, but not only for computing the value function, but you can also use it for finding the maximum possible value you could get across any policies, right? So you could do this V pi S, expected value RT plus 1 plus V pi gamma times V pi ST plus 1, and now if you put a max here, max over all possible actions, in some sense you are getting independence of the policy pi, and so you get this equation 4, right? And this is what you are solving in your lab assignment, right? And this is the value iteration algorithm. You start with some random initialization of the V's with the hope that when the iterations converge, the t plus 1 iteration of V will be the tth iteration of V. Okay,